You'd recollect that towards the end of the previous video, while using the vegetation index-based tassel cap technique on a particular area of interest, the Satabhaya village in East India, I had encountered a difficulty in extracting the shoreline. The topography was complex. There were several water-related features on land near the coast, such as streams and rivers, which made it difficult to get the shoreline in a single piece. There were numerous line segments, and to isolate and join them manually would have been cumbersome. With the water index based and automated shoreline analysis and extraction tool developed within the European Coastal Flood Awareness System project by the Copernicus program, we will not encounter a similar issue. And in this workflow, I will demonstrate it. The SAET algorithm is adapted from the ShoreX technique of extracting the shoreline from optical imagery, and it has a sub-pixel level of accuracy. Yes, while the Landsat and Sentinel bands are no less than 10 meters per pixel, the root mean squared error of using SAET algorithm has been shown to be not more than 3 meters. Besides the efficiency, the process of shoreline extraction is also completely automated, facilitating ease of use besides other advantages. You can refer this paper on mdpi.com to read more about the process. ECFAS's shoreline analysis and extraction tool is open source. Only recently was it made accessible to the public on July the 3rd of 2023, and it can be downloaded from zenodo.org. As of today, version 4 of the tool is the latest version, and it comes wrapped in a 150 MB zip file, which I have already downloaded. So let me show you the contents of the zip file and an overview of how to install it and things to take into consideration while doing so. Within the zip file, there are a couple of folders, the report folder and the version 4.0 tool. In the report folder, there is a PDF which we will refer to, and in the version 4.0, there are several files and folders within. Preferably, you must extract the content straight away directly in the C drive in order to avoid complications. Within the version 4.0, there is a doc folder which contains a couple of PDF on the installation steps as well as a README document, and we will refer all the 3 PDFs together in a moment. So first, let's visit the installation document. All the instructions are very lucidly mentioned, and if you follow it, you will not encounter an issue. So Python 3.9.7, that particular version needs to be installed for this particular tool. Thereafter, you will have to create a virtual environment BAT file as well as download the SAET libraries using the pip command line mentioned. Also, in the file sp_config.py, you will have to input your login credentials to download the Landsat and Sentinel satellite imagery, which forms the input in this particular tool, and the procedure is relatively straightforward. On USGS, which is the repository for Landsat imagery, you'll have to place a request to access machine-to-machine interface API. It takes usually 1 day to get this particular approval for Landsat imagery, and for Sentinel, you'll have to go to dataspace.copernicus.eu and just create a login on that particular website for you to be able to access it from the command line interface of SAET tool. So this is the sp_config.py is a Python file, but it can be opened in a notepad, and there is a provision to input the username as well as the password as indicated in the installation PDF file. In case you encounter difficulty in downloading the SAET Python libraries manually in the previous step, you can automate the process here by running the appropriate GDAL Python wheel based on your operating system. Also, here in the home folder, there is an example of use_sp text file, which contains the Python script formats for the search, downloading, and processing of Landsat and Sentinel optical imagery. This is a very useful file for future reference as well. If the installation was done correctly, you will now be able to run the virtual environment to download the Sentinel and Landsat imagery. SAET_env_activation is the BAT file that you had created earlier, and the environment has now been created. In this particular workflow, we will use only Landsat imagery, and I will demonstrate it to you. I have not used the Sentinel imagery because it is only downloadable for the European coast. And our area of interest is on the east coast of India in the Satabhaya village. And therefore, Landsat imagery is only what we'll use. Let me show you the other PDF file which comes with the tool. It is the proof of concept for the ECFAS SAET tool. Very detailed document, and the table of contents is visible. It's about the project, about method of defining a satellite derived coastline, optical as well as radar imagery, the previous methodologies, what are its advantages, disadvantages, and how basically SAET tool helps to navigate the disadvantages and generate a better outcome. So, and it contains the previous research work, the output on Mediterranean coast, the root mean squared error information, as well as the parameters to run, what all the acronyms mean, so on and so forth. So it's a very detailed document, 166 page document, and is useful for running the particular tool. In the output underscore data folder, there is a folder where all the downloaded data is accessible, both the raw data for the Landsat 8 and Landsat 9 satellites, as well as Sentinel-2 satellite, as well as whatever processing we do. The shorelines are also saved in the SDS folder within the data folder. Besides, there is a website on YouTube, or link on YouTube, ECFAS module, SAET Shoreline Analysis and Extraction Tool. It's a 26-minute video. And while it is based on SAET version 1.0, it is still very useful for referral because it's in a video format and very step-by-step with detailed instructions on not only what is SAET, how basically has it been developed under ECFAS, how to install it, what are the prerequisites, what are the basically the modifications that you have to do, how to run the tool, and as well as how to basically post-process as well as analyze the particular imagery, which is useful. So far in our previous workflows, we have not analyzed the output in terms of what extent the erosion or accretion is there, but we can do that impact analysis using the post-processing steps after running the SAET tool. And those instructions are also mentioned here, and I'll demonstrate it as well. Right. Before we run the Python script to search for and download and process the Landsat imagery around the Satabhaya village on the east coast of India, by running the Python script on the virtual environment, we need to do one additional preparation step. In the aux data folder in our home location, there is a beach polygon shapefile, and we need to edit this shapefile on ArcGIS Pro. The premise is simple. This particular tool, SAET, was developed by European Coastal Flood Awareness System. This particular body basically is in charge of monitoring the European coastline in the case of certain climate-related events such as a storm, flooding events, and therefore the software comes preloaded with the beaches polygon around the European coastline only. What we need to do is add this particular shapefile onto ArcGIS Pro, and we will add the beach polygon around the area of interest which we want to basically download the Landsat imagery for. So this polygon serves only one purpose, which is to basically restrict the software to basically extract the imagery from the online portal for that particular location. So it need not be geographically accurate. It just needs to overlay the area of interest. Let me update the base map on ArcGIS Pro to satellite imagery view from the current topography view. And if I switch off, you can see the outline of the beach underneath the beach polygon. And if I click on the polygon, you can see that it has a beach code attached to it. So there are a total of 8,170 beach polygons which come preloaded with the software package. But none of them are on the Asian or Indian, you can say, coastline. They are mostly on the European coastline, and some of the nations are in and around Africa, where European nations basically have a governing interest. Therefore, let me begin by adding a particular polygon for Satabhaya, and for that I need to first locate it on the map. This is its location. We just need to create a new polygon, so we'll go to the Edit tab and click on Create, and we'll draw a polygon around this particular location of our area of interest. I am not being very particular about the dimensions or the scale. I'm just drawing a polygon around it right now. We need to save the edit in order to save the particular polygon. And if I go to the attribute table now, a new row has been added for this particular polygon, but currently it is empty. Besides the shape dimensions, it is empty. So we need to plug in the buffer distance 300 and the beach code. So this part is the most crucial one. You need to add a unique beach code, which is currently not mentioned. So 8193 is the next in the sequence. So I'm adding that as a beach code. So this is the fundamental step that we need to do. And now we are in a position to run the particular script on the virtual engine. So the name of this particular Landsat imagery where I had faced problem earlier in the NDVA tassel cap, the imagery dates from the 2024 3rd of January. And there is also a code, which is the identifier mentioned in the name of the particular imagery raw file. So when I go to the examples of use text file, underneath the searching for Landsat imagery, the parameters which I need to enter are central date, which I want to monitor, and two bordering dates, beginning and ending around that, a cloud level percentage, and the type of product which I want to do. And the scene identifier is the six digit number which is used to identify the scene. So this is the only input parameters that we need to work in, and this is the particular code by which we will tweak that code to search for the Landsat imagery of our choice. So let me copy this particular code and paste it in a Word document so that I can show you how to edit it subsequently. (139.046) is the identifier. And because I know which date of imagery I wish to download, I don't need to basically, and just let me show you that on Earth Explorer USGS website. This is the product that I'm referring to. It again has the same identifier. So I'll replace the current default identifier mentioned with the identifier, product identifier of our choice. Ensure that there are no gaps between the digit and the function command. Subsequently, I know I have to put the start date, central date, and end date. So typically, when I know the date of imagery that I want, the start date and end date can be 1 day above and below the particular central date. So my central date is, I've inputted that. In terms of cloud cover, I know that the cloud cover is less than 1%, and in optical imagery, as you would know by now, that we don't need cloud cover. It will basically tamper with our workflow. So we need to put as minimum cloud cover possible. Fortunately, we know that our imagery of choice has a cloud cover of less than 1%. So upon entering this particular information script onto the virtual environment, the software begins to search on the USGS portal via our API that we had requested earlier and got approved, and it shows me the search result. This is the exact same product. It is currently showing as product number 0, which is the same as what we want to download. As you can see, the product name is one and the same. So it basically gives us a visual cue by showing us the search result, whether this is the particular imagery we wish to download. So our search results were accurate, so we can now proceed to download the Landsat imagery. So for that also, a particular Python script is mentioned in that text document. We need to run this script and also specify what is the number of the unique identifier number of the image. So let me demonstrate it to you. This is the script. So as I run it, it will ask me which of the search result you want to download. So currently there is only one search result with the name 0. So I just need to input 0 and enter, and the imagery will begin to download. The actual length of download depends on your server bandwidth, etc. But then it's a typically this file is 945 MB and it will download it in full. And once it is completed, I am fast forwarding it. It will unzip it and place it in our output folder under the data section. And I'll show it to you where it has downloaded. It is exactly the same output. If you would have downloaded it manually from USGS website, the output is stored in the exact same format under the Landsat folder. So I had done some previous working, so those workings are from there. But then there are two satellites, Landsat 8, Landsat 9. So in the Landsat 8, you can see that our product from 3rd of January 2024 has been loaded and all the imagery bands are there. And we now need to process it. And the best part of running this SAET tool is that we don't need to use any software. We just need to run another script and the software will basically internally process it and just generate the output of our choice. So this is the processing script that we need to enter with a particular parameter, which is what is the segmentation. So if you're aware, we used to do thresholding. We used to select a water index in one of our previous workflows. I'll just show you what it is about. So there are several types of water radiometric indices. We had experimented with the MNDWI before. NDWI is natural difference water index. This is modified normalized water index, MNDWI, and the advantages, disadvantages are mentioned. And AWEI, which is automated water extraction index, is what we are going to use because it has certain advantages which could be beneficial for us as it removes the shadow pixels and so on. So this SAET tool runs predominantly on SWIR, which is shortwave infrared band. The algorithm is based on that, and I believe that we can use the AWEI NSH as our processing method basically. The parameters which we need to enter besides that segmentation method is our area of interest beach code, which is optional, but it is preferable to do so because it will reduce the time of processing. So let me paste that code. We just need to change MNDWI, which is the default parameter. It's not a default parameter, it's mentioned in the script currently. I'll just change it to AWEI NSH. And in the beach code, if you remember, in our polygon, the new polygon which we had created, the beach code which we had inserted was 8193. So that is the reason why we need to remember it, and we'll plug it in once again onto the script so that the portal will only search for images which are underneath, which has an intersection, you can say, with this particular beach polygon. Subsequently, it will ask us and which image to process, and we'll have to enter the number. Let me paste the script in the Python virtual environment and run it. There are currently 4 output, 3 from Landsat and 1 from Sentinel in my data folder. 3 of them are from my previous working, so I'll have to be specific which particular file which I want to process. So it is the dataset number 1, which is from 3rd of January 2024, which I want to process, and I'll enter number 1 in the parameter and it will begin processing it. The processing steps take some while to perform. I am just fast forwarding it, but you can see the steps involved. Water index band, cloud max computation, water index mass, rough pixel line, read projection, clipping, rasterizing, extracting points, averaging it out, and so on. So finally, once the processing is done, the shoreline shapefile is saved in the SDS folder. SDS stands for Satellite Derived Shoreline, and the folder is preloaded only on the tools folders. Under output data, there is a SDS folder, and the output has been generated and stored in this particular folder. So now we can, now that we have processed, and what we should have as an output is a shoreline, which is underneath the polygon of our choice on Satabhaya village on the east coast of India. Let me open ArcGIS Pro once again and load the shapefile. There are 2 shapefiles, the line shapefile and the point shapefile. Both of them would be of use to us. Let me just load the line shapefile first. As you can see, there is a clear, distinct shoreline which has been generated. Isn't this marvelous? The output from my previous workflow, there were dozens and dozens of line segments, but this one looks like a single shoreline. Not that it is completely accurate. You can see that some of the shoreline portion is extending onto the land area as well. We can modify it if we want to at a later stage, but the most important point is once I open the attribute table is it's one single shoreline. So I don't even need to join two different line segments together. It is one single shape. So this is one major advantage of using this particular tool. Now, I also wish to show you the shoreline on the prevalent, or you can say the satellite imagery during that particular time frame. So I am just exporting this particular layer file because the base map satellite imagery, I don't know from where exactly it is. I can find it out, but then it's unlikely to be from 2024 January. So I wish to see the shoreline on the correct, you can say, proportionate satellite imagery. So I'll just export the layer file to KML. This KML file, I can load it onto Google Earth. I've named it as test, and on Google Earth, the benefit is there is a possibility that you may get to overlay the output on a base map from that particular timeline, and we'll try to do so. You can see that our KML file has been loaded and the shoreline is on the Google Earth base map. The imagery date, it's a stitch. This Google Earth base map is done via stitching multiple imageries. So the imagery date in our, you can say, area of extent is located on the bottom part of the screen. You can see the current imagery date is from the 4th of September, 4th of August of 2023. So I'll just play around with the imagery timeline to see if there is any imagery from January of 2024 on this extent. Around Satabhaya, I don't see anything, but then I can just navigate around the shoreline to see if I can spot the correct imagery base map from that particular timeline. Let me hover a little bit towards the south. You can see the imagery date right now is from February 2024. And this is much closer to January 2024. So let's examine the coastline closely. Is it accurate? I had indicated to you that the pixel value is typically within, there is a root mean square error of 3 meters per pixel. So currently, if my assessment is the shoreline is reasonably accurate around the coast. Remember that this is a water index, and in the water index there is a slight bias that semi-water, semi-land features. The shoreline will be on the seaward edge of the particular feature. So more or less, in my opinion, the shoreline is reasonably accurate. Intuitively, it is logical to validate the shoreline which was extracted from optical imagery using the optical imagery raw dataset itself rather than scouring for appropriately timed base map on Google Earth or other platforms. So let me try it out. I've imported the B4, B3 and B2 bands from the Raw Landsat 8 imagery from where this shoreline was extracted. These three bands can be composited together here on ArcGIS Pro to generate a true color, that is a natural photograph view of the terrain. So let me click on imagery, raster functions, and under the data management section, let me click on the composite bands geoprocessing tool. So within this, the input rasters will be the three bands B4, B3 and B2 respectively. And these three layers can be combined together as a composite to generate a new layer which would look like a natural photograph, as you can see on the screen over here. And we can use this to basically visually inspect whether the generated shoreline is accurate or not. So as I navigate across the screen, you can see that where the blue pixels end, that is where the shoreline has been generated. So broadly speaking, it is appearing reasonably accurate. One doubt which one can have is what are those white pixels and whether that should be constituted as land or sea and or not. So this is something which we can validate it. So how we will do that? We'll just switch to SRI's default satellite imagery base map, although it is from a different timeline, but we can see in a much more clearer manner because this imagery is of a much higher resolution. So we can understand the properties of the area and then try to discern from our generated composite layer whether the shoreline is accurate. So over here you can see that there is this stretch of the land, there is a white pixel, and as I toggle the views, it is very evident that there is a beach over here. So naturally the beach will not be formed as a part of the coastline, so the edge of the beach will be held as the coastline. So the rendition appears accurate. So let me just go to another section of the shoreline. Over here there is a high density of water pixels, and let me toggle the views. So over here again you can see that the beach feature is extent of the beach feature is where the coastline is drawn, and waves and other aspects which are, you can say, light white pixels, those are on the sea. So those are correctly not utilized for the shoreline. Therefore what we can conclude is that the NDWI index derived shoreline from Landsat is reasonably accurate. Now in parallel I've also downloaded an imagery from 25th of December 2020, so which is around, you can say, 3 years ago. I'm not showing those processing steps. I've just generated using the same steps the shoreline, and I'm just loading it side by side. So now we have two shorelines where we can basically compare. Now previously we used to do visual comparison. This time we'll take it one step forward and do some actual quantitative analysis, which is gonna be fun. So the red colored shapefile is the shoreline is from 2020, and the yellow one is from 2024, and you can see that there is erosion around the coast, which was also indicated by the news article which we were referring to. The Satabhaya coast has been ravaged by coastal erosion, which is basically hampering that fishing village. I can do a rough and measurement. So you can see that at this particular zone there is a 55 meter gap between both the shorelines. But then in order to do something which is scientifically can be held as a valid output, we need to do something better than this. So let's proceed to do that. Now this particular processing step, I will do it on QGIS, not on ArcGIS Pro. So in order to do that, we need to first, I would prefer to clip the shoreline. So I don't want to do the analysis on the entire shoreline. What I'm doing is searching for Satabhaya and will clip the shoreline to a particular, you can say, extent around it only. Let me measure the shoreline extent. In this particular view, that is. So half the image view is around 1000 meters. So roughly speaking, if I were to extend it, it would be around 2000 meters of shoreline would be something which I will demonstrate it to you, how to do some quantitative analysis of the extent of erosion, or if there is accretion, we can measure it as well. So in the output file, there was a line file and there was a point file as well. So the point shape file, we'll just load it onto ArcGIS Pro. The analysis has to be done using this particular point data. So the point is the actual output from the tool, and the line is basically, you can say, a segment which basically links all the points together. There are thousands of points right now in that particular shapefile, and we'll now clip it. And in order to clip it, what we will need to do is to create a polygon for clipping it. Prior to that, let me add the point file from 2024 as well. So now the point shape files of the shoreline from both the timelines have been added onto ArcGIS Pro. Once again, we'll just clip around 1500 to 2000 meters of the shoreline, and I'll demonstrate the analysis portion to you on QGIS. I'm going to databases beach_polygon and creating a new feature class, which will be my beach extend polygon, which I will clip the point data set. I'll just uncheck Z values, which is the height values, and just go to the final step, finish it. The raw dataset, empty dataset has been generated, and I'll create a polygon now by clicking on the create button underneath the edit tab. So around the shoreline of our choice, I have just created a rectangle, and now I'll use the clip tool to basically clip the point data set. I have not saved this new file, so it's very important that whenever you create a new polygon or edit a file, you hit the save button, and not on the main save button, but underneath the edit tab. So I'm just doing that. In the input feature or dataset, I am first clipping the dataset from 2020. I'm using the beach extend polygon as a clipping feature, and I'll name the output dataset as per my choice. December to 2020 _ clip. The output has been generated. And let me repeat this same clip geoprocessing tool on the 2024 dataset. Right, both the clipped point shape files are there, and I'll just close all the other layers so you can see the clip has worked out successfully. Now there are only 260 points. Earlier there were in thousands. Now only 260 points are there in one layer from 2024, and 243 points are there from the other layer. So how do we go about doing the quantitative analysis? First, let me export these clipped files as shape files so that I can load it onto QGIS. However, before that, I need to do one additional step. As part of the quantitative analysis, we need some reference line to basically measure the extent of change. So I have just created a new empty line shape file, that feature class I have added. Even before drawing that particular line around the shoreline, I'm just modifying its symbology so it appears prominent. Now I'll go under the edit tab. I'll create this particular feature. So the name of the line feature is reference line of the inner beach. So I am basically drawing a line on the inner side of the beach, very close to the shoreline, but whose boundaries extend beyond the shoreline, both at the beginning and at the end. So I've created that line feature, and as you can see, it extends beyond the shoreline. The idea is to divide the reference line into equally spaced line segments and subsequently measure the distance between the shoreline points from both the timelines to the nearest sector on the reference line. After this step, we can average out the net of the distances to find the mean accretion or erosion level for that particular sector on the reference line. So the first step which we need to do is go in the edit tab and click on the divide tool. I had used the split tool earlier, that was incorrect. We have to use the divide tool. As you can see that there are three ways which we can divide based on distance, parts or percentage. We'll divide it into 10 equal parts. So the line which is reference line, which is around 6,500 feet or 2 kilometers or 2,000 meters, I am dividing it into 10 equal parts. So now the entire line is divided into 10 different line segments, as you will see from the attribute table, and each line segment has a length of around 183 meters. So now we have created those segments, and we also have our clipped shoreline points, and we can now export this as shapefiles to be loaded onto QGIS. But prior to that, just one last step. We'll create one new column called DLFID_INT in the reference line shapefile. What the reason we are doing it is for a subsequent processing step, and after we have created that particular column, we'll just name it as it's basically a unique identifier for each of the individual sectors. So we'll name it as 101 to 110, basically 1 to 10, but above 100 is the identifier. So this will be the unique, you can say, code given to each and every sector, and we can use it subsequently to identify what is the mean erosion or accretion for each of this uniquely coded sectors. Done. We have done so, and we'll save the edits. We'll right click data, export features, type in the name and location of our shapefile. I have already created a test folder on my desktop, so I will save the contents over there. It is important to suffix the name with a .shp, which is a shapefile format, for the export features to save it as a SV shapefile format. So I have exported the reference line, which I had divided into 10 equal parts, as a shapefile. Now I will do the same. I'll export the shapefile for the January 2024 shoreline points. And finally, I will do the same step for the December 2020 shoreline points. All our three input layers have been exported as shapefiles. So now we can open QGIS and load these particular shapefiles and process it further for quantitative analysis. Let me close ArcGIS Pro and open QGIS. I am using QGIS 3.4 version, but you can, I think, use any of the versions, older or newer, to perform the same quantitative analysis. Once QGIS has opened, I will load the three files, shapefiles. I'll sort the folder by type and the three shapefiles. I'll just click all of them together and paste it in the layers pane. And I'll also, underneath XYZ tiles, I'll add the OpenStreet base map. One can also have a satellite imagery base map over here, but I'm not being too picky. Moreover, I'll do the final, you can say, symbology and artistic endeavors on ArcGIS Pro, because I'm much more comfortable using that particular software, as it gives us
more, you can say, functions, features, and there's an attractive quotient about it. The first quantitative analysis step that we'll do is to use the distance to nearest hub points tool. So in the source points layer, I'll select the shoreline points from 2024. In the hubs layer where all my sectors are there, that's the ref line layer, I'll click on it. And in the hub layer name attribute, which I'll basically use the DLFID_INT, that particular column which I had inserted in the last step of ArcGIS Pro. I'll save the file as DTH 2024 and I'll run it. The output has run successfully, and I'll just repeat the same step for the December 2020 shoreline points, and subsequently I'll show you the output as well. So this particular tool helps us to find the distance between the shoreline points to the nearest segment on the reference line. In the output attribute table, focus on the newly generated hub dist column, which contains the distance between the shoreline point to the nearest sector on the reference line. Total 260 shoreline points were there in this layer, and hub dist has been computed for all of them. And in the other output, total 243 points are there, and hub dist has been computed for all of them as well. So now we can proceed to the next step, but let me just make one edit, because the newly generated layer output has not been named correctly due to some technical glitch in my QGIS software. I think I'll just remove the two layers and reload them so that I can easily visualize the output as per the year. So 224 and 2020, both the layers have been added once again with the correct names onto the QGIS layer panel. The next step is to summarize the results, which is the hub dist, based on the sector name. And in order to do so, there is a particular tool which we will use. It is called statistics by categories. So over here, what we'll do is use the 2024 distance to nearest hub output layer. We'll calculate the statistics based on the hub dist, which is the distance, and the category is the hub name, which is the name of the sector. So we are just summarizing the results to each sector on the reference line, that is. I'll save the file as category statistics 24, short of it, catstat24, and we'll run this particular tool. Before showing the output, let me repeat this same step for the 2020 layer. Once again, I will summarize the hub dist, and the category which I will summarize it to is the hub name, which is already there in the parameters. I'll just rename the output and save it to the desired location and run the tool. Both the output has been generated. Once again, both the layers have basically the same name. I'll just remove it and just add it back once again so that I can distinguish between the 20 and 24. The correct layer names, file names have now been mentioned. Let me show you the output. So in the output, against each of the 10 hubs, the total number of count of points which are attached to it, as well as the mean distance of the total number of points is distance to that particular sector is also mentioned. So we are just only interested in the mean at the moment, and you can say partially the count, but mean is the most important column. The rest is not of that much importance to us. For the other catstat20 also, the result has been generated in the same format. Now finally, we will use the join attributes by field value tool. We'll use this tool twice. So firstly, we'll use both the layers now. We'll join both the layers. So we'll use catstat20, the older layer, as the input layer, and the input layer 2 as catstat24. The field name, which we'll summarize it, is by hub name. And what we are essentially doing is doing a, you can say, comparison between the output of both the shoreline points. So we'll use a prefix called post underscore, which will help us to distinguish 2020 from 2024. I'll just save the file of the output and hit the run, and I'll just show you the result, which will be easier for you to interpret what we are essentially doing by using the join attributes by field value processing tool. Let me open the attribute table. Now what has happened right now is both the layers have been joined together as per the hub name, which is the common denominator. The columns with the post as a prefix belong to 2024, whereas those without it belong to 2020. So we are interested in basically taking a difference of the mean distance from 2024 to 2020. So as a result, we'll just hide all the remaining columns and let only the post underscore mean and just the mean column, which is from 2024 and 2020 respectively, be at the front of our eye. Thereafter, using the field calculate tool, we'll create a new column, we'll name it as difference, and the formula is subtract post underscore mean from the mean. So we just need to type that out, and QGIS will automatically calculate the values for the entire 10 rows, which are basically for all the 10 hub names. What is the average difference of the mean? You can see the output preview minus 3.69. So which indicates for the first row, the difference is minus 3.569 equals to erosion, that is. So a figure in minus in 2024 minus 2020 indicates erosion, and all the 10 rows has a negative value. So you can see for each of the 10 sectors there is erosion. Not a single sector is unaffected, nor has any sector along that 2 kilometer coastline that we had shortlisted has accretion between 2024 January and 2020 December. Now I'm just creating a new field in this same attribute table. Because the field has been named hub name by the formula, I have to rename that hub name to DLFID underscore INT. So all I have done is made that new column and linked it to hub name. Now that the hub name DLFID INT has been integrated, I'll just use the join attribute by field value again tool. All what I am doing is linking the reference line layer to the previous layer output, with DLFID underscore INT being the common denominator. Remember that the reference line layer we had inserted the DLF unique identifier in the ArcGIS last processing step. So because hub name was not part of that attribute table, so we use this particular tool to essentially join both the layers using this, which will aid us while we are doing the symbology. So if I go to the layer property of the newly generated output, and instead of single symbol, I use it a categorized symbology. I categorize it by DLFID underscore difference column, which is the erosion levels. And I'll put a color pane, a color ramp, let's say light red to dark red. And then classify. So by default, 10 classifications have been generated. And you can see for each of the sector, what is the erosion level. The darker that reference line, which means greater that erosion for that particular section of the shoreline. Now I prefer, as I had indicated to you earlier, to use ArcGIS Pro for the symbology because it gives me a wide variety of options and it is also user friendly. So in order to do so and in order to make the output much more presentable, I am just exporting this joint layer onto ArcGIS Pro. So I'll export it as a SRE shapefile. Let me load it on ArcGIS Pro. I hope you understood the importance of using QGIS and how quantitative analysis helps to generate more meaningful results. Previously, we had done visual analysis, basic level of measurements, and so on. But this time we are doing a proper, you can say, quantitative analysis. And frankly, if we had made more sectors, we had just used 10 sectors, which are with a large size, 180 meters each. If we had used we had split the reference line into much more sectors, then our analysis would have been much more quantitatively better. The output would have been even more specific, that is. So what we can do after loading the newly generated reference line, we'll just symbolize it as per the category. So I'll use the graduated colors. In ArcGIS, you get a ton of color options. You get to decide the method of classification, the number of classes, and all of it in a user-friendly manner. I'm sure QGIS also has the same features, but ArcGIS Pro is much more, in my opinion, much more user-friendly. So I prefer to use it. So you can basically classify it as per equal interval or quantiles or standard deviation and so on. Personally, I even create my final output maps using this particular software. So it becomes all the more important for me to do the final stage of post-processing on ArcGIS Pro. So I'll not take you through these steps. I'll do it behind the scenes, but I'll just show you the output final map, which could be very useful as a presentation material as well. So this is the layout, and I'll just make few modifications. This is the final output. You can see the mean erosion across the coastline, bit from 1 to 10 meters, and the stretches, the sectors on the reference line has been color coded accordingly, and the location on the map, the inset, the scale, and everything, the name of the output, where it has been sourced from, everything is mentioned in the final output. I hope you enjoyed the impact analysis stage of the demonstration just as much as the autonomous extraction of the shoreline using the SAET tool. Thank you.